Okay, folks. Are there any further questions arising on that previous material? Okay, if not, I'll move on to the last shortish lecture for today, which is to say something more about the different types of memory and memory management that are available. And this more on memory lecture. Specifically, I want to say something about managed memory, constant memory, and shared memory. So far, we have seen device global memory, which we've allocated on the host via explicit CUDA malloc, and such a pointer is available to both host and device to perform reads and writes via explicit CUDA memcopy. There's a good reason to introduce those because I think it gives a clear picture on what is really happening. But specifically if you're interested in CUDA, that may not be what you do in practice anymore. However, in other models, it may be what you definitely do need to do. We've also seen some rather small kernels where we've introduced some local variables, typically loop indices. So these variables would be private on a per thread basis. So each thread has an independent copy of such variables, and those would typically be expected to be held very close to the compute end, that is in registers. However, there are some other types of memory available in CUDA. The first one we're going to talk about is this thing called managed memory, and this basically is a convenience which provides a unified address space between host and device, so you can get rid of basically having a host pointer and a device pointer and just have one pointer which you can access in both places. And also with managed memory, you do not need to perform any explicit copies. This can be a very useful feature if you're just developing code and want to try things out, and where code becomes significantly more complex, and having explicit CUDA memcopy becomes quite time-consuming to develop and introduce in code. The second thing we'll have a look at is what's referred to as constant cache memory, or just constant memory on the GPU. And this is a special little bit of memory which is read-only in the kernel, so no writes allowed. And that lack of ability to do writes means you don't have any cache coherency issue with this, and the result is you can have a constant memory which is fast and effectively high bandwidth. And then finally, there is the issue of shared memory. So that is memory which is shared between different threads in the same block. So this is often declared statically in the kernel, although it can be arranged as part of the kernel launch to do it dynamically, and just exists for the lifetime of the kernel and is used to marshal and reuse data in the kernel if so needed. So let's have a look at this managed memory first. So what we've done so far in a sort of schematic picture is we've allocated some memory on the host via a malloc. We've done allocated memory on the device by CUDA malloc. And then we have to do this business of copying back and forth between host and device to move data. And then we get to the point of the kernel, we definitely need the device pointer. So that's actually in some ways slightly tedious, and it would be nice if we could just do something like this. So I could imagine having a single allocation against a pointer here, excuse me, which I might want to initialize on the host and then just use the same reference to get into the kernel. So CUDA does provide a mechanism to do this, and it's called managed memory. So the appropriate allocation for managed memory would be to call this CUDA malloc managed, and there's my managed memory pointer, and I want to allocate a certain number of bytes. So that piece of managed memory is now available in a single address space which I can refer to on both host and device. So that's, and there is no explicit memcopy here. So the magic here is that the CUDA runtime will manage, so it's called managed memory, the transfer of the data when it detects that it is needed. So that's the CUDA malloc managed API call. So that call is made on the host, and it returns a piece of memory which is managed, and copies between the host and device are handled by the CUDA runtime. Such memory is typically released with the standard CUDA free when you need to release resources. So what's going on here is basically a process of migrating pages of memory as access to memory is required. So if you're on the GPU, say, and you make an access to an address which the CUDA runtime believes it hasn't got up to date, it generates a page fault, so-called, and this then initializes a copy of the relevant data from host to device. So it should be understood that these copies still occur, and therefore you have the same overhead of doing the data transfer, and actually an additional overhead in this management procedure. So the time taken can be relatively slow compared with a simple CUDA mem copy. The trade-off you're making here is it's much simpler to develop a piece of code. There are a number of facilities available with managed memory to improve performance. Potentially, one can define a prefetch, an asynchronous prefetch. So if you as the programmer have allocated some managed memory and you perhaps initialize it on the host, and you know that at some point in the future this is going to be required on the device, you can issue this asynchronous prefetch via CUDA mem prefetch async, and this is saying I want so many bytes at that address to be transferred to the device there. There is another mechanism to provide hints to the CUDA runtime about what is going to be the pattern of accesses to particular memory. So this is CUDA mem advise, and there are some special values associated with this advice argument. So there are things like CUDA mem advised set read mostly. This is saying this piece of memory is going to be mainly read from, maybe occasionally write to. So this advice doesn't actually perform any action, it's just giving hints to the runtime about what the likely patterns of access might be. And so it is possible to improve performance. So that's managed memory. For CUDA, pretty much a standard thing now. It should be remembered that so for example, if you wanted to have an AMD GPU, that there has historically been no analog of this managed memory, so you're back to explicit mem copy type approach. Okay, here's this second type of memory. This constant GPU memory can be useful in some circumstances. Here's the Fortran example. So in this Fortran example, sorry, I'm talking nonsense. This is the C example. Here's the constant memory introduced via this special memory space qualifier double underscore constant double underscore. And constant memory is usually declared at file scope in C, so it's static there. And so if you want to assign some values to that piece of constant memory, there's this special CUDA memcopy to symbol API call, which is a bit like CUDA memcopy, except it's loading these values into this constant memory, and those coefs in this example can be accessed in your kernels if they are in scope. So here, for example, if you're doing some computation that occurs very frequently, it may be advantageous to get fixed data into this constant memory. So access is fast rather than having it in global memory. Here's the Fortran. So the analogy is there's a special attribute for the declaration constant. Here at the top there, again, this would typically be at module scope in Fortran. And again, because the compiler now knows that that has been declared to be constant memory, assigning values to it at runtime is just a Fortran assignment. Again, that's just the analog of the kernel which accesses those coefficients. Okay, a couple of things to note about this constant memory. A relatively scarce resource. GPU might have 64 kilobytes in total. So this is obviously not a place for huge lookup tables or anything of that nature, and it actually must also be available to accommodate the kernel actual arguments for your kernels. So in times past, if you had a kernel function with an immensely long argument list, you could actually run out of constant memory because you had too little constant memory to accommodate the arguments. And any overflow will just get spilled out to global memory with a corresponding penalty in performance access time. So that's something you can use if needed, and is there to be used. So the final thing we want to have a think about for today is the issue of shared memory. So anybody who's done any shared memory programming in the context of things like OpenMP knows there are a series of potential issues related to shared memory, so this must be treated with some care. But the idea is that this shared memory is available to all the threads in a block, and it allows cooperation between them. So it might be useful for storing some temporary values on a per block basis, particularly if those values are going to have significant reuse in the kernel. You can use the shared memory to marshal data within a block if you need to shuffle data around. And if you think about it, you can also use shared memory to perform reduction type operations, which depend on individual per thread values. So if, for example, you wanted to compute a sum, the contributions of which are worked out on individual threads, you can add up the total in the block by using shared memory. So the issue with shared memory is typically one of synchronization. So when is it safe to update shared memory requires synchronization, and the basic synchronization API call in CUDA for threads within a block is this double underscore sync threads. No double underscore at the end, you'll notice there. And that says that all threads in the block must reach this point before any can continue. So the declaration of shared memory is via this double underscore shared double underscore memory space qualifier in C, and adding a shared attribute in the declaration in Fortran. So I think here we have an example of a kernel which is going to use some shared memory. So I've got this integer array TMP of a certain size, which I've hardwired in here, and that declaration has this double underscore shared double underscore memory space qualifier, so that temp variable is shared between all threads in the block. Okay, so the idea behind this particular example is to take the elements in the argument myArray and reverse the order so that the result is the same array but in reverse order. And this because we're doing this for shared memory in a block, we'll just consider the case of one block here. So if we look at this, what we've declared our thread index to be index, and we are making the basically saying we're going to move the contents of my array into this temporary array, and then we copy them back in the reverse order at the end. So at this point in this lecture, I usually look at the audience and say, what's gone wrong here? Can anybody see?
An index +1.
I think that's okay in C. I think that's okay.
I also believe that's correct.
So the first thread will have index 0, so that should go into threads per block -1 in the reverse order in the C picture. So it's something I referred to in the previous slide.
I think you're going to be reading from my array in some part right into my array and other threads at the same time.
Yes, this is the potential, well done, this is the potential issue here. There is a potential, because this is now shared memory and these threads are all executing independently, we have a potential issue. So let's suppose I am thread 0. I can make copy index 0 of my array into temp. However, in the meantime, another thread may also have the last thread may also have copied its value into my array. So I have a potential race here, and what do I need?
You need to synchronize.
Yep, I need to make sure that copy into the temporary array has occurred on all threads before I start shuffling data around. So that's a slightly subtle issue if you haven't come across that before, but that's the classic synchronization issue in shared memory programming. Okay.
A good word to remember is then. Whenever you say then describing your problem, your algorithm, you have a problem.
Yeah. Again, shared memory is a relatively scarce resource. There are perhaps something like 50 kilobytes per block. So there are mechanisms to inquire at runtime about exactly how much resource you have. There are various other performance considerations which I don't really want to get into for this. So there is if you've come across things like false sharing in OpenMP, where different threads are invalidating each other's caches, then there may be some similar problems in the CUDA. Okay, so I think that's the last slide for today. So the exercise, there are, you certainly welcome to continue with the previous exercise if you're still working on that, but there are some additional exercises to try and have a look at the managed memory. So the managed memory is just really asking you to revisit one of the previous working examples and replace the explicit allocations and copies by managed memory. And then there's a couple of simple exercises on constant and shared memory. So if there are no questions, please feel free to continue with the exercises. And the scheduled close is 5 o'clock. So we'll be here to 5 to help with any questions. But failing that, the restart tomorrow morning is 10 o'clock Greenwich Mean Time. Mark says he's fixed the Fortran problem. Yes, I thought that there was a suspicious amount of commented out code in that.
Please do send a pull request to the Git hub.
Yeah, I also have to load the math library for Fortran and include the lib command. I put them in the Etherpad at the very beginning, what I changed for Fortran.
So there's a question here. Are there any specific CUDA memory instructions for managed memory in the context of GPU direct? So by GPU direct here, this is a technology which allows direct, part of it is related to hardware and provides fast connections between GPUs within a single host, and there are also elements which allow communication between GPUs on different hosts in a sort of distributed memory picture.
And I/O, don't forget.
And thank you, yes.
Sorry.
So are there specific instructions? It may depend on precisely what you're trying to get at here. I don't think, do you have something specific in mind.
So if I remember correctly, GPU Direct is quite a low-level technology. So if you were writing the CUDA runtime drivers, you might use it. Or if you were writing a device driver to make your network card be able to do RDMA directly to the GPU, you would use it. But as an application programmer, I don't think there are many cases you would use it yourself. Is that about right, Kevin?
Well, it manifests itself in my view. It manifests itself in things like can you do MPI with device memory references?
Yeah, so it's really your MPI implementation would have to use GPU Direct to enable that to work. Is that?
So I'm not. So the whole sort of philosophy of the managed memory is you don't have to explicitly do anything.